Hello students, in this lecture we will just introduce the term, that is look at this table. I will give the idea first, then I will start. Actually we are comparing the steady state error and constants that we have studied, position error, then velocity error, acceleration error. So we are calculating all these things with the generalized transfer function, and we are varying this value of n. Okay, so that type of the system will get changed. So look at this. See here, this is generalized form of the transfer function. Okay, g of s h of s is equal to k is constant k into s plus z1 s plus z2 upon s raised to power n s plus p1 s plus p2. Okay, so numerator will give you number of zeros when you will equate it to 0. And denominator will give you number of poles. Okay, so look at this term, this s raised to power n is there. Okay, in previous transfer function we have taken the term m, that is nothing but a constant term. You can take any term there. Okay, but the concept will be same. When you will put here n is equal to 0, I told you that when n is equal to 0, s raised to power 0, it will be 1. So what you will conclude? No pole at origin. Okay, again I am repeating, what is type of the system? Type of the system is nothing but number of poles at origin. If there are no poles at origin, what you will say? Type 0 system. If one pole is there at origin, so that is type 1. Okay, and so on. So see, we will start. First of all, we will consider for type 0 system. So for type 0 means no pole at origin. In that case, we will substitute n is equal to 0 here. Look at this, n is equal to 0. So this term will be 1. Okay, or you can say that no term is there, only k into s plus z1 s plus z2 upon this denominator. Okay, so now start. So steady state error we have seen for position error constant, we have derived the formula ESS is equal to 1 upon 1 plus Kp. Okay, so see, we know the formula for Kp. What is Kp? Limit s tends to 0, g of s h of s. Okay, so we have substituted Kp here with the formula. Now see what we need to calculate. What I am doing, g of s h of s term is there. Okay, I am substituting this transfer function here. Okay, I am substituting this transfer function here. And for type 0 system, see, for type 0 system, I am just putting here n is equal to 0. So we know that s raised to power 0 is 1. So you can check that your transfer function will be replaced with this transfer function. Okay, and when you will take limit, see, there is no s in numerator and no s in denominator, so it will not cancel. Okay, so this term is as it is. Okay, so Kp is given with this formula and the steady state error is given with 1 upon 1 plus Kp. Okay, now next, ESS is equal to 1 by Kv. We have seen this for unit ramp input. Steady state error for unit ramp input is given by 1 by Kv, and the constant that we have introduced there, that is called as a velocity error constant. And formula for velocity error constant is, look at this, limit s tends to 0, s into g of s h of s. What you need to do, see, you need to concentrate only on this term g of s h of s. See, now you will again replace this g of s h of s with this term, but here s term is there, that is in the formula itself. Okay, so when you will take limit, okay, here s is there in the numerator. So when you will take limit of s tends to 0, so it will be 0. So what you will get, see here you will get Kv is equal to, look at this, here Kv is equal to 0. Okay, here this part after taking limit, this denominator is 0. What is that denominator? This denominator is nothing but Kv. So what you will get a value of Kv? Kv will be 0. Okay, here what we are getting, Kp is as it is with the formula whatever we have shown, and steady state error is same, that we will show with 1 upon 1 plus Kp. Here as s term is there, after taking limit we got Kv is equal to 0, and look at this, 1 by 0 it will be infinity. Okay, so steady state error ESS here we are getting as infinity. Okay, next steady state error is equal to 1 by k. See what we are doing, we are calculating this steady state error with kp, kv, k, but for type 0 system, okay, and type 0 system is there, so there is no term here, no pole at origin, okay. So look at this again, what is formula for k? This is formula for k, we know that s square into g of s h of s, so you will substitute this g of s h of s here, okay, but there is a term s square in the numerator, so when you will take limit, again this term ka, it will be 0, okay. See this term ka, it will be 0 because s square term is there. So what will be the value of ESS? ESS is equal to 1 by 0, it will be infinity. 1 by 0, it will be infinity. So steady state error because of parabolic input we are getting as infinity, okay. See these are the values for type 0 system, okay. So this is the table, okay. So actually what I will do, I will substitute the value there. Look at this, kp for type 0. What we are getting, kp is same as that of kp with the formula, okay. This kp is as it is. What you need to do, you need to substitute the formula, limit s tends to 0, g of s h of s, okay. What we got here, kv we got as 0, so I will put here 0, okay. What is k? K is also 0, so I will put here 0, okay. Now ESS because of kp, look at this, ESS because of kp, what I got here, the same formula 1 upon 1 plus kp, okay, because we know that kp is as it is, we got some constant value there, okay. ESS because of kv, look at this, what I got, ESS because of kv, I got the answer as infinity, so I will put here infinity. What I got here for k, I got infinity, okay. So here I got kp 0 0, 1 by k, 1 upon 1 plus kp, infinity infinity. So we have calculated all these 6 terms for type 0, okay. Now let's see for type 1 system. Look at this, for type 1 system what I will do, I need to put here n is equal to 1, so this is the term here s, okay. So when I will put here n is equal to 1, so this term is nothing but s raised to power 1. So what is your conclusion? This is type 1 system because one pole is at origin, okay. So we will repeat the same thing whatever we have done for type 0 system, and we will calculate all the 6 values, okay. So type 1 is equal to, look at this, formula will be same formula, okay. Only thing we need to calculate here, this g of s h of s is changing, because of that the s term in numerator and denominator will get cancelled out and your answer will change, okay. So look at this, ESS is equal to 1 upon 1 plus kp, okay. But see here we have replaced this kp with the formula, same, we have replaced with the formula of kp, so 1 upon 1 plus limit s tends to 0, g of s h of s. Now what I will do, I will substitute the value of g of s h of s. So what is value of g of s h of s? Look at this, this is g of s h of s, but there is a term s in denominator of the transfer function. So what will be there? See here there will be the term, I am writing, see suppose I will replace this g of s h of s. So what will be my formula here, k into the numerator bracket, same, s plus z1 s plus z2, and here there is a term s, again this bracket will be same, okay. So what I am getting here, there is a term s in denominator, so when I will take limit, so what will happen, this term will be 1 by 0, this term will be 1 by 0, okay. So see what I am getting here, value of kp, so I am writing here value of kp is equal to 1 by 0 is nothing but infinity, okay. So see here 1 by 0 is infinity, so ESS for unit step input, it will be 1 upon 1 plus infinity, I am writing here 1 upon 1 plus infinity, okay, because I got kp as infinity here, so 1 upon 1 plus infinity, okay. So again 1 by infinity it will be 0, okay, 1 by infinity it will be 0. So I hope you are getting. Now next the formula ESS for unit ramp input, okay. So ESS for unit ramp input is given by 1 upon 1 by kV, okay. So see I am substituting the formula for kV here, 1 upon limit s tends to 0, s into g of s h of s, Okay, so what I will do here again, I will replace this g of s h of s with this transfer function. So what is that transfer function? Here there is a value and there is a term s. Okay, so see here this s and s will get cancelled. Okay, there is a term s, so s will get cancelled. Okay, so what I am getting here, after taking limit, there will be some constant value. Okay, so what I am writing here, ess I am getting some constant value as kv. Okay, kv will not be 0, kv will not be infinity, because as this ss will get cancelled, after taking limit I will get some constant value. So that constant value is given with kv. Okay, so steady state error because of kv is given by 1 up by kv. ess is equal to 1 by kv. Okay, now third one, ess is equal to 1 by k, that is for acceleration error constant. Okay, and we are calculating acceleration error constant for unit parabolic input. Okay, so look at this, this is unit parabolic input. I have substituted here the formula. Now I will replace, this formula is s square g of s h of s. So look at this, I am replacing that with the above transfer function, and there is a term s in the denominator. Okay, so look at this, this s and s will get cancelled, but there is a term s in numerator. Okay, so when you will take limit, so this term will be 0. So what I will get here, look at this, ka, this part, denominator part, after taking limit will be 0. So I am getting ka as 0. Okay, so steady state error will be 1 by 0 is nothing but infinity. Okay, now I will put again all the values here in the table for type 1 system. Okay, so look at this, type 1 system is there. I am substituting the values. Look at this, here type 1, what I got here, value of kp I got as infinity. Okay, value of ka sorry, I will put directly first the ess because of kp. So what I am getting, ess because of kp I am getting here 0. Okay, so here ess because of kv I am getting 1 by kv. So I am writing here 1 by kv, but here you can see that here I am getting the constant value. So kv I will write with constant value. Okay, then ess because of k I am getting infinity. So I am writing here infinity. And what value I am getting for k? K is nothing but 0. Okay, so see here infinity kv 0. Okay, 0, 1 by kv, infinity. So I hope you are getting the concept, and same thing is done for type 2 system. Okay, so I will simplify. You can calculate for higher order. Okay, or for type 4, type 5 also, and you can complete the table. We need to conclude from this table. So look at this, this is type 2. So what is type 2? In case of type 2, number of here you need to put n is equal to 2 there. Okay, so here I will put n is equal to 2. Okay, for type 2. Then look at this, here again the formula ess is equal to 1 upon 1 plus kp, then 1 upon 1 plus, look at this. Okay, so this term you can check that when I am calculating kp and I will take limit, as there is a term 0 here. Okay, so what will happen here, kp will be here after taking the limit, this term will be 1 by 0 is infinity. Okay, look at this here, 1 by 0 is infinity. So complete term 1 by infinity is 0. Look at this, 1 by infinity is 0. Okay, similarly here kv is there, so I am substituting the formula for kv, s into g of s h of s. I have replaced that g of s h of s. Here s and s will get cancelled, but there is a term s in the denominator, and when you will take limit, so again what you will get, kv is equal to here 1 by 0, that is nothing but infinity. Okay, so this 1 by infinity is 0. Again next, ess is equal to 1 by k. Okay, so what I am doing, I am substituting the formula of k. Look at this, here s square will get cancelled. Okay, because the formula is limit s tends to 0, s square g of s h of s. Okay, but for type 2 here s square term is there, so this s square will get cancelled, and you will get some value of k. This term will be some constant value. Okay, therefore ess will be again some constant value. Okay, so I am writing the type 2. So what I am getting here, look at this, kp is infinity, you can cross check, I am writing kV is also infinity, but I am getting some constant value of K. Okay, so ESS because of Kp is actually 0. Then next again, because of kV is 0 and because of this is actually Ka. Okay, so see, next you can calculate for type 3. Here I have not shown, but you can calculate and you can cross check. So type 3 answers I am writing here: infinity, 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 0, 0, 0. Okay, so now look at this table carefully. Okay, here type of the system is actually increasing. Okay, and look at this transfer function carefully. Now I am replacing this 2 with n because this is generalized form. You know that I have introduced the term type of the system here. You know order of the system. So what is order of the system? Order of the system is highest power of s in denominator. Okay, so you can check here, if the type of the system is increasing, order of the system is also increasing. Okay, look at this. If I will put here 1, so that s will be multiplied with this. Okay, so if type of the system is increasing, I am writing if type is increasing, order will also increase. Okay, so what you need to do, look at this, as type of the system is increasing, order of the system is also increasing, and you know that if order of the system is increasing, so it will be difficult to calculate or comment on the stability. We know that as order of the system increases, so system will be more complex. Okay, so I will conclude here, type of the system increases, order of the system also increases, so stability of the system decreases. Look at this, stability of the system decreases. But what about the steady state error? Look at this, if type of the system increases, you can check here in type 3 these constant values are infinity, but what about the steady state error? We are getting 0. Okay, so steady state error decreases. Okay, again, as type of the system is increasing, order of the system is also increasing, so stability of the system is decreasing, but steady state error is decreasing. Okay, so I hope you got the concept. Okay, with increase in the type of the system, order of system increasing, stability is decreasing, and steady state error is decreasing. Okay, so we will solve numerical based on steady state analysis. Thank you, students.